Hello, I'm going to talk about the challenges on the road to FAIR+E research data and how the concepts of semantic units and knowledge graph building blocks could help on this road. And since I only have 15 minutes, I'm only able to touch on these two concepts briefly. Now, FAIR stands for Findable, Accessible, Interoperable, and Reusable Data and Metadata, and it should be data and metadata should be fair for humans and machines alike. And that's a challenge, and a feasible Go FAIR strategy is to use semantic technologies because they provide URIs. There is the possibility for semantic searches, and ontologies and graph language help with the vocabulary. Semantic technologies come with challenges, and FAIR+E, E stands for explorable. And one of these challenges is that users usually do not want to look at large complex graphs, but FAIR requires data to be machine actionable, and machines cannot handle fuzziness and need contextual information that humans often do not need because they can make it up for themselves. And that brings us to a dilemma that the more one pushes data representations towards machine actionability, the less human readable they become. And here's an example. We have a simple statement, a weight measurement with a confidence interval, and you see how complex the graph becomes. And only these parts of the graph are actually relevant for a human reader, and everything else provides the context needed for a machine to understand the graph or the data. So this dilemma represents an impedance mismatch, and data storage should be decoupled from data representation. And we need new approaches for making graphs more explorable for human readers so that irrelevant information can be filtered out. The next problem is that RDF, OWL, and property graphs are highly expressive and therefore do not automatically provide fair data. So in addition, we need adequate data models that must be applied consistently, and developing these models requires semantic expertise, which most users and developers do not have. So to counter that, we need openly available and reusable graph patterns. Another problem is somewhat related to the other one, that most developers and domain experts do not know graph query languages like Sparkle and Cypher, and also do not want to learn them. So what we need in addition is also reusable query patterns. Another problem is that making statements about statements using graphs data is challenging, especially when the statement comprises several triples. So we need a way for intuitively partitioning the data graph into semantically meaningful, identifiable subgraphs. And the last problem or challenge that I see, at least, is that data and metadata standards are usually domain-specific and often change over time. So here is an example for a simple statement of a weight measurement, and you see two graph patterns that are frequently used. So what we need is we have to decouple data storage from data access by providing flexible data exports. So now to the semantic units and what they are. So semantic units partition the knowledge graph into identifiable and semantically meaningful sets of triples, and these subgraphs then form units of representations or short semantic units. Each semantic unit is represented in the graph with its own resource, a node, and its own unique identifier. And you can refer to this semantic unit when making statements about its contents by using the identifier. This allows in a very intuitive way to make statements about statements. Each semantic unit is an instance of at least one semantic unit class, and the class's definition specifies the type of information that its instances contain. The classes are organized hierarchically, resulting in an ontology of semantic units. So semantic units summarize the contents of a knowledge graph and can be used for profiling the graph. Semantic unit classes provide another entry point for querying and exploring the graph, searching for a specific type of information. Semantic units can consist of other semantic units, resulting in different representational granularity levels. I distinguish 7 different basic categories of semantic units, each with its own set of subclasses, but I cannot go into detail here. Semantic units provide a new framework for aligning graphs, subgraph matching, for visualizing search results in a table, for modeling negations and cardinality restrictions for instance graphs, so on the A-box level, and for documenting and relating ontological and discursive information. Now, how could we implement semantic units? Well, in a property graph like Neo4j, it's very simple. All nodes and relations belonging to a particular semantic unit can be identified by having the same key value pair, like for instance, the key assertion URI and then the identifier of the specific assertion unit. In RDF and OWL, a semantic unit can be organized like a nanopublication using named graphs. And semantic units can be implemented to form FAIR digital objects within a knowledge graph. And then they comply also with the EOSC Go FAIR strategy. And with semantic units, we can establish what I call FAIR+E. So fair and explorable knowledge graphs, because we can not only explore the contents of the knowledge graph by the conventional ontology classes, but in addition to that, also by semantic unit classes. And these can be also organized across representational granularity, like for instance, we have the level of triples, then on top the level of assertions, of topics, of entries, and then the graph as a whole. And this can be used for accessing the data. So you could have a navigation bar here to the left with an entry with several pages. These are all topics, and each topic can have several assertion units contained in it. And to the left, to the right, you can then display the selected content that you selected here to the left. Or you could have a split screen where you have to the left the graph, and to the right a form-based display, and then you can select a node or relation in the graph and see the contents in the form-based display to the right. And here you can also switch between different levels of representational granularity, from triples to assertions to topics to entries. And then the information will be filtered and only shows the information relevant to that specific level or layer. Now, what are knowledge graph building blocks? A knowledge graph building block is a knowledge processing module. And each type of semantic unit has its own building block. And these can be combined, and together they manage a knowledge graph application. The building blocks implement semantic units, and with them organize the data into FAIR digital objects. And they provide a common graph pattern for a specific type of semantic unit, resulting in FAIR+E data and metadata. And here's an example for a storage pattern for a weight assertion, weight measurement assertion. And you see the main idea is to always be able to reconstruct the original user input, or the input for that assertion. And here 2 different types of inputs are distinguished: a unit class or unit instance and a float value. And when the application can reconstruct the input, the input could always be mapped to other export formats. Like for instance here, the OBO format and the OBOE format, which are used in the biomedical and in the ecological domain. And you see how these resources from the from the storage pattern can be mapped to the export patterns. Further export schemata can be added anytime by using the building block editor. And building blocks also provide predefined cipher and SPARQL queries for finding data belonging to that type of semantic unit. And users then can combine these from different types of semantic units, like Lego bricks, to create more complicated queries without having to write cipher and SPARQL themselves. The editor will allow the specification of new building blocks and will allow adding new export schemata for existing building blocks. Each building block is independent of all other building blocks, but they can be linked so that a semantic unit can instantiate another semantic unit. Their general modular architecture allows for reuse of individual building blocks by making them openly available so that third parties can specify their own knowledge graph application by combining different building blocks and creating new ones. This is a general overview or schema here for the example of a parthood assertion building block. It provides input template, it provides export templates, it provides a complex data structure together with Jinja templates, and that provides the HTML for the front end. And in the back end, the data could be stored in a graph or in a semantic table, so in a relational database. Now, I developed a small side project, a Python Neo4j-based proof of concepts for the building blocks, a scholarly knowledge graph, and that's a crowdsourced knowledge graph. And the idea is you add a DOI here in the web interface, and then the application fetches the metadata from Crossref, generates an entry semantic unit with some topic semantic units, showing the metadata. And you see here, it's a human readable data representation is completely decoupled from the machine actionable data graph by using Flask templates, the Jinja 2 templates. Here you have the underlying data graph. Each semantic unit has its own node, and this is the actual data, which is based on a model for modeling scholarly information that we've published before. Now you can add some, here you're at the research result page, and you can add what the research result is about. Then we have this resource here that has an instance label, class label, and ontology acronym. This indicates that it's an assertion. You can now make statements about this assertion unit. For example, you can specify the confidence level of that statement, which is valuable information for identifying citation distortions. And here I added some more content, a head and two eyes, and the application automatically identifies that a granularity tree exists in the data, a parthood-based one, and now you can visualize this. So it filters the general data graph and shows only the partonomy. And what I cannot show because I don't have the time is it also has versioning, editing history for semantic units and input nodes, and search results can be shown as a table. What it does not cover is the exports feature. It doesn't have a building block editor, and there's no flexible storage options. Now the conclusion is for the first problem that the building blocks and semantic units decouple data storage from data presentation and provide a new framework for exploring the graph. So we don't have the problem with users having to deal with very complex graphs. The second problem, the high expressivity of RDF, OWL, and property graphs, is also dealt with because the building blocks provide storage and export patterns that guarantee FAIR+E data and metadata. The third problem, the lack of developers and domain experts with semantic expertise and knowledge of query languages. The building blocks provide reusable query patterns, so this would be solved as well. Then the problem of making statements about statements. Semantic units provide a way for intuitively partitioning the data graph into semantically meaningful identifiable subgraphs. So this would be solved. And last but not least, the building blocks decouple lean data storage from data access and provide flexibly expandable data exports. So domain-specific data standards and evolving data standards can be dealt with as well. Well, that's it. Thank you for your attention.